There we go. Let's see. Get that going. Can anyone not hear me? Give it a second, see if anybody can't hear me. Okay, looks like we're all right there. So I'll circle back and say, anybody got anything they want to say? Okay, then I'll move that to, has anybody got a question about the class or a comment? Well, we have a couple things we should talk about. So I'm just going to start sharing my screen and we'll look at Blackboard and we'll talk about some of that stuff. So when is the final? Well, I don't know. Let's see. What does it say here on my calendar? That's not a week. How about here? Okay, you guys are on Wednesday the 13th at 12 o'clock. So let me yeah, that's a interesting idea. Okay. Anyway, agreed. Oh yeah, well, yeah, I can appreciate that feeling. Yeah. I got a feeling I'm going to get that from everybody in the room right now. Okay, but yeah, that's when it'll be. It's on Wednesday. So let me think. That'd be 2 weeks from today. So now, sapling issues. A few people have been having issues at logging into sapling, and I've been I I really gave the sapling people a hard time about it because we're running out of time here and we can't have anything going crazy. So what I've been able to determine is some of the browsers have been updated. They said that Chrome has been updated, although that's what I use and I've had no problems. But anyway, so that prompted the suggestion that if you can't log in, then try a different browser. So if you're using Chrome, you could try Firefox, you could try Safari. If you're really want to be risky, you could try Internet Explorer, but then your computer will get a virus. So anyway, or there's a whole lot of other, I shouldn't say a whole lot, but there are some other odd browsers out there you could try. But anyway, I'm not saying go out and try to find a different browser. Just if you have another one loaded on your computer, you could switch to that one and see if that fixes it. Other thing that they were trying to blame was that Blackboard had some updates, which I don't really think so. But anyway, there's nothing you guys could do about that one. So anyway, I finally got this one really nice guy at Sapling that got back with me, and he gave me his personal cell phone number. And so, and I got his email. So anyway, if anybody's having trouble logging in to Sapling, if that comes up at all, please send me an email as soon as possible. Toss in a text message too, so I can get on that right away, and I will contact him, and then he will get with you. He'll do like a video chat with you and get you going. So I don't think there should be any more problems with Sapling. So because he will fix it. So anyway, if if you encounter any of that stuff, just let me know as soon as possible so I can put you with him. Then, as people were alluding to, exam 4. I had been debating this for a while, but I think to preserve the original grading structure for the class as much as we possibly can, we need to go ahead and have exam 4. And we're still not going to be doing the research project, but we added a lab, so that sort of balances it out. Anyway, which is the lab we're doing today. Okay, exam 4 is going to be Friday, May 8th. So that will be a week from next Friday, I think. Is that right? Yeah, but well, no. Yes, no. Get my calendar going again. Let's see. Oh, okay. This Friday is the 1st. So yeah, it'll be a week from this Friday. It will not be 2 weeks. It'll be 1 week from this Friday. So anyhow, and it'll cover Chapter 5, Thermochemistry, and Chapter 6, Electronic Structure and Periodic Properties. It will not have anything from, Chapter 5 and 6. It will not have anything from Chapter 7. So just, it'll be 5 and 6 will be the main thing. Be a few questions from Chapters 1 through 4. Be able to do everything on the presentations, Chapters 5 and 6, and be able to do everything in the worksheets for Chapters 5 and 6. And there might be a few questions from the sampling assignments. So hopefully that's pretty clear. Anybody got a question there? Yeah, May, what's up? Okay, so will the final exam be cumulative? No, the final will be cumulative and, yeah, as you say, cumulative report. It will cover everything. Oh, my connection is poor. I will turn off my camera. Okay, anyway, yeah, it will cover all the chapters. It'll be evenly distributed between the chapters for the final. Anybody else got a question? It'll be like what we would have done had all of this crazy stuff had not happened. Except we can't use the American Chemical Society's standardized exam because of copyright issues. They will not let us put that into electronic format. So I have to make an exam. But it'll be similar to what they would have done. How long is it? Well, I don't know for sure, but the original exam was 70 questions. So I think this will probably be 70 questions. I'm going to try to stick with something as similar to what you would have done otherwise as I can. I can't use the same questions though because those are copyrighted. Anybody else? Would be similar to the pre. So yeah, you guys did the ACO standardized pretest. That's sort of that's the way, okay, that's the way the ACS exam questions are, but I think probably what I will come up with will be more like what I've done for exams 1 through 3 and then exam 4. So, I mean, it's still going to be the way I write the questions. I'm not going to write questions exactly like theirs because then I'd be violating their copyrights. So. Anybody else? Okay. So now looking at sapling, because of all the craziness with some people not being able to log in, I moved some of the due dates a little bit more. So now let's see, chapter 6's stuff is on May 2nd, And that, I believe, is Sunday. Let's see, is that right? May 1. No, I think it's Saturday. Excuse me, it's Saturday. So, and then it just sort of goes from there. The not for credit practice drawing molecules is also due on that date. And then the chapter 7, which is chapter we're in right now, is 2 days later. And then chapter 8 will be 2 days after that, which that won't be very many questions at all. And then the gas chapter, chapter 9, will be on, see, the due date will be, I believe that's Friday. Yeah, that's Friday. Yeah, Friday, May 8th. So that'd be a week from this Friday. So it is getting a little tight on getting everything in. I'm sorry. But hopefully, if you were able to get into the sapling homework, you've already done chapter 6. So that's really not, an issue. I have not looked to see who has done any of this. So I don't know. Okay. Is there any question on any of that stuff? I don't see any. So then I guess we should just go to the lab today. This is our last lab. We'll still have class next Wednesday, but it'll just be like a lecture kind of thing instead of a lab. So to get to the last lab, I know everybody knows how to do this, but click on course materials, go down to lab reports, click on lab reports. Oh, wait a minute. Let me change this just to make sure this is working right. I'm going to put it in the student view. Okay, so one more time. Course materials, go down to lab reports. There's the lab we're doing, ideal gas law simulation. So this activity is a simulation of the relationship of temperature, volume, pressure, and the number of gas molecules in a sample. Those are all related to each other, and they're related through the ideal gas law. This simulation also demonstrates the relationship of kinetic energy and molecular speed to temperature. And then you've got a link to the simulation, and then it says, after completing the instructions in the attached file, prepare a laboratory report with these sections: title, date, partners. You got 1, 2, 3. You got 5 data tables. The 4 parts of the ideal gas law are broken out in Gay-Lussac's, Charles's, Boyle's law, Avogadro's law. So that's just the ideal gas law broken into 4 pieces. And then the last data table is for kinetic energy and molecular speed. And then you've got some observations that I want you to make, and so that'll go in that section. And then I have some discussion questions that you should be able to answer after having done the simulation. And then your comments. So usual kind of stuff. So now let's take a look at the instructions. So I'm going to click on the ideal gas law simulation attached file. And so it looks like this. In this simulation, we'll explore the relationship between moles of a gas molecule, the volume it is contained in, its pressure, and its temperature. We will also look at the speed a gas molecule moves at in relationship to its temperature. This relationship is also reflected in the kinetic energy of the gas molecule, since kinetic energy is energy in motion. So we're looking at the motion of the gas molecules. I'll go to this link to open the simulation. I'll do that in a second. You may need to allow Flash to run on your browser, and that will depend on your security settings on your computer. Excuse me. To operate the simulation, press the heat button to start heating. Press it again to stop heating. The same works for cooling your gas. There's a stop button, but it's quicker just to hit the heat or the cool button a second time to stop it. You will not be able to hit a particular value. You'll get close. Like if you're going for 300 Kelvin, you can probably stop it at 310, or you can stop it at 290 or something, but you won't hit right on 300 unless you're just lucky. Otherwise, so it doesn't matter, because we're going to be looking at what relates to whatever temperature you arrived at. Okay, so it doesn't matter if you hit exactly on the temperature you're going for. There's a piston in the container that holds the gas, and you can move that piston up and down. That's going to change the volume. If you move it up, you increase the volume. You move it down, you decrease the volume. So you press the up button to raise the piston and increase the volume, and again to stop, you press the button again to stop the piston. Otherwise, it just keeps going. You press the down button to lower the piston and to decrease the volume. So now we've got the ability to change the temperature, to change the volume. If you want the volume to not change on its own in response to the conditions of the experiment, then you click on the lock next to the up and down buttons, and then that will lock it. You can add gas molecules to your container by clicking on the pump handle. Every time you click on it, it adds the same number of molecules. You could count the molecules, but they're moving around pretty fast. Well, I guess if you want, well, I didn't think about it till now. You could drop the temperature all the way to 0 Kelvin, in other words, absolute zero, and then you could count the gas molecules. I didn't think of that till now, so you could do that. Otherwise, we'll just say that there is some number of gas molecules, and you can increase that number by clicking on the pump handle, and which you will need to do. And you can keep doing that until you hit some kind of an arbitrary particle limit. Really, there isn't a limit, and you got two different gases that you can use, gas A or gas B, or you can make it both, gas A and B, if you want to. And as far as what you do with that, it's not going to change your outcome. If you have one gas or the other gas or a mixture of gases, everything's still going to work out the same. If you want to release gas molecules out of your container, there's a valve right below the pressure gauge. You click on that. Each time you click on it, it releases the same number of gas molecules. And I don't know, that might be the same as the number of gas molecules that the pump puts in. It probably is, but I didn't check it out. Now, the different experiments you're going to do. First one's going to be Gay-Lussac's law. Start with the pressure at about 400. No, excuse me, start with the volume at about 400 liters, and then you lock the volume. Record the temperature and the pressure in a data table. Then raise the temperature around 100 degrees. So you start at, I don't know, say you start at 300 degrees Kelvin. Then you put it to 400. Whatever you start from, just add 100. And then you record the new temperature and the new pressure. And you repeat that at approximately 100-degree intervals. So you get a set of data, and then you make a graph of the pressure versus the temperature. Then you're going to do another experiment, Charles's law. This time you start with the temperature at about 300 Kelvin. Unlock the volume. So you allow the volume to change in response to your other parameter. Then you record the temperature and the volume. You raise the temperature about 100 degrees, record the new temperature and volume, repeat at 100-degree intervals, produce a graph of volume versus temperature. Then you're going to do Boyle's law. Start with the temperature at about 300 K, the volume at 1,000 liters. Lock the volume. Do not change the temperature. Record the volume and the pressure. You don't care about the temperature. Decrease the volume by about 100 liters. So you're going to go from 1,000 to about 900. Record the volume, the new volume, and the pressure. Repeat at approximately 100-liter intervals. Produce a graph of pressure versus volume. Then you need to go back and produce another graph of the reciprocal pressure, 1 over P versus volume. Because you'll see that if you do pressure versus volume, you will not get a straight line. You'll get a curve. Curves don't really do much for us. So you want to get a straight line by doing reciprocal pressure. Next experiment you're going to do is Avogadro's law. Start with the temperature at about 300 Kelvin and the volume at about 500 liters. Lock the volume. Record the pressure. I didn't say anything else, but you could say, well, you could record the pressure and say that it's, if you know how many gas molecules, you could put that number in so that you've got the pressure versus the number of gas molecules. Then you click on the pump one time, record the volume. Repeat that 4 times, produce a graph of pressure versus the number of times pumping, or you could do pressure versus number of molecules. Okay? Either one will be fine, because I'm not sure you can count the molecules. But if you can do that, that would be sort of necessary. And then next experiment is going to be kinetic energy and molecular speed. Start with the temperature about 300, it should be a big K, 300 K, and lock the volume. Record the temperature and the average kinetic energy in kilojoules per mole, and the RMS, that's the root mean squared molecular speed in meters per second. RMS stands for root mean squared, but anyway, that's sort of, anyway, don't worry about it. Just call it RMS. Raise the temperature about 100 degrees, record the temperature. Wait a minute. Record the temperature, or raise temperature about 100 degrees, record the temperature. I don't know what I was trying to say there. Basically, you're going to raise it 100 degrees each time and record the kinetic energy and the molecular speed, or RMS. So then, under observations, what do you observe about the motion of the gas molecules if the temperature is increased? Then you've got 5 discussion questions. What is the relationship of pressure to temperature? How many times you repeat? You repeat until it will not let you repeat. There are limits on the numbers, so you can keep adding. You know, say if it's the temperature, you can keep adding 100 degrees about, but eventually it stops at, I believe, 600 Kelvin, so that you won't be able to go any higher. Okay, so you're going to do these relation questions. Volume to temperature, pressure to volume, pressure to number of molecules, kinetic energy, and molecular speed to temperature. And then that's it. So now let's look at the simulation. So I'm going to click here, and here it is. So, you know, this is kind of cool. Let's say I want to raise the temperature. I can click here to heat it, stop, and if you were watching the pressure, well, wait a minute, excuse me, the pressure will stay the same, and the volume will increase. Now, if I lower the temperature back down, and now I lock the volume. You see, I clicked on that lock, that'll lock the volume. Now I can heat it up some and stop, and the volume is locked at 320, and the pressure, you can see, is increasing. And, you know, you can do all that stuff. Now, let's say we want to put in more gas molecules. I can click on the pump, and it put in more. And if I want more, I can do it again. I can do it again and do it again, and just keep going crazy with the pump until finally it's going to say particle limit. It won't let me put any more in. If I want to let some out, I can click on the valve right below the pressure gauge. You can be watching for that. Here we go. Oh, you see it let some out. I can let out some more, and I can let out some more, and so on. So that's like getting a leak in your car tire. And if I want to put in additional gas molecules, I can go over here and click on gas B, and I can unclick gas A. I don't know if it'll let me do this or not. Let's see. Oh, it will. Okay. So you can see those gas molecules look different. So we're having a real crazy party inside our container here, all of our gas molecules. So anyway, that's the way that works. Can't think of anything else, folks. Anybody got a question? I'll stop sharing the screen. Okay, so I'm going to be starting up the simulation. If you see that I put you in the wrong group, let me know. I'll move you. I got a couple people that came in a little. Excuse me, I just got a weird text. I got a couple people that came in later. I need to put them in their groups, and then we'll get going. How do I graph? You can, Google spreadsheet. I don't know, honestly. See, I was sort of thinking you'd be able to get access to Excel. I'll research that and get back with you while you're doing the experiment because I really don't know the answer to that. Okay, got a couple more people. Oh, I think I just put someone in the wrong group. Yeah, I did. Can't do that. Okay, I got one more person. I'll make sure I've got everybody in here. That should be. Okay, I think I have everybody in the right place. And so I'll be hitting the button here to start the groups. So here we go.